What specific problem does HYPERSTEER aim to solve in the context of instruction-tuned language models? And what are the limitations of existing methods, such as prompt engineering and parameter-efficient fine-tuning, that HYPERSTEER addresses?
HYPERSTEER aims to solve the problem of reliably controlling the outputs of instruction-tuned language models, LMs, by generating effective steering vectors that enhance model performance without modifying or adding parameters. Existing methods like prompt engineering face challenges such as user jailbreaks, forgotten instructions, and robustness issues, while parameter-efficient fine-tuning requires significant modifications to the model. HYPERSTEER occupies a middle ground by combining the scalability of unsupervised methods with the targeted control of supervised activation steering, thus addressing the limitations of both approaches. It leverages hypernetworks to generate steering vectors conditioned on both the steering and base prompts, allowing for more precise control over the model's behavior. This innovative approach enables HYPERSTEER to outperform previous state-of-the-art methods even on unseen steering prompts, demonstrating its effectiveness in enhancing instruction-tuned LMs.
How does the proposed HYPERSTEER method work? Please illustrate the algorithmic steps involved in generating steering vectors using the hypernetwork architecture.
The HYPERSTEER method operates by utilizing a hypernetwork architecture to generate steering vectors for a base language model, LM. The process begins with the hypernetwork, denoted as H, which takes pairs of input and steering prompts, XS, and maps them to steering vectors, delta_x_s. The hypernetwork consists of multiple layers and employs a residual stream representation for each layer, allowing it to condition on both the steering prompt, S, and the internal activations of the base LM, B, when processing the base prompt, X. Specifically, the best-performing variant incorporates a cross-attention mechanism that uses the hypernetwork's residual stream for attention queries while leveraging the base LM's residual stream for keys and values, enhancing the generation of steering vectors. Finally, the generated steering vector is added to the hidden vector, H, of the base LM to produce the steered output, effectively guiding the model's behavior according to the specified steering prompt.
Can you provide a simple yet illustrative example of how HYPERSTEER generates a steering vector for a specific base prompt and steering prompt? Walk through the process step by step.
HYPERSTEER generates a steering vector through a systematic process involving a hypernetwork that takes both a base prompt and a steering prompt as inputs. For instance, consider a base prompt like explain how to sort lists of numbers, and a steering prompt such as output using C++ programming syntax. First, the hypernetwork, H, processes these prompts to produce a steering vector, delta_x_s, that is added to the hidden vector, H, of the base language model, B. The hypernetwork utilizes the internal activations of the base model and the steering prompt to condition the output, effectively tailoring the response to align with the desired programming syntax. This approach allows HYPERSTEER to generate a steering vector that not only modifies the model's output, but also maintains coherence with the specific requirements of the steering prompt, demonstrating its effectiveness in targeted control.
What are the practical benefits of using HYPERSTEER compared to existing methods such as REFTAR1 in terms of efficiency, scalability, and performance on unseen prompts?
HYPERSTEER offers significant practical benefits over existing methods like REFTAR1 in terms of efficiency, scalability, and performance on unseen prompts. It demonstrates improved compute efficiency, requiring fewer flops to maintain evaluation loss as training data increases, making it more economical than REFTAR1. In terms of scalability, HYPERSTEER combines the advantages of unsupervised dictionary learning with the targeted control of supervised activation steering, allowing it to effectively handle a larger number of steering prompts during training. Performance-wise, HYPERSTEER's cross-attention variant outperforms all supervised activation steering baselines on unseen steering prompts, showcasing its ability to generalize better than previous methods. Overall, HYPERSTEER not only matches but also exceeds the performance of traditional prompting methods, making it a robust choice for instruction-tuned language models.
How was HYPERSTEER validated during experiments? Please discuss the datasets used, experimental design, and metrics for measuring its performance against baselines.
HYPERSTEER was validated using the AXBENCH dataset, which included a total of 16,000 steering prompts sourced from Gemascope sparse autoencoder, say, feature labels, and a diverse instruction pool. The experimental design involved training and evaluating HYPERSTEER on two specific datasets: Concept 500 High, which contained 500 steering prompts seen during training, and Concept 500 Ho, which included 500 unseen steering prompts for testing. The performance of HYPERSTEER was measured using a harmonic mean of discrete scores across three dimensions: adherence to the base prompt, adherence to the steering prompt, and text fluency, collectively referred to as steering performance. Additionally, HYPERSTEER's performance was compared against various baselines, including fine-tuning, activation steering, and prompting methods from AXBENCH, with a particular focus on the state-of-the-art activation steering method REFT-R1. The results indicated that HYPERSTEER outperformed previous activation steering methods, even on held-out prompts, demonstrating its effectiveness in generating steering vectors.
What were the key results achieved by HYPERSTEER, particularly in comparison to other methods, and what insights can be drawn from these results regarding its effectiveness in practical scenarios?
HYPERSTEER demonstrated significant advancements in steering performance, outperforming the previous state-of-the-art activation steering method from AXBENCH, even on held-out steering prompts that were not seen during training. Notably, it matched the performance of steering via prompting, which had previously outperformed all activation steering methods. The results indicated that steering performance scales logarithmically with the number of steering prompts used during training, showcasing HYPERSTEER's scalability, akin to unsupervised methods while maintaining the targeted control of supervised approaches. Additionally, the cross-attention variant of HYPERSTEER excelled in generalization to unseen steering prompts compared to other supervised activation steering baselines. These findings suggest that HYPERSTEER is not only effective in controlled environments, but also holds promise for practical applications where adaptability and performance on unseen data are crucial.